Another example of rate law, this time I have three reactants colliding with each other, highly unlikely, but it's a good practice in calculations. The temperature is given to remind us that the K is constant at a given temperature. That's a disclaimer. So let's look at questions. The first question is, what is the rate of formation of Z in trial number 3? If you look at trial number 3, the rate of Y is given. And if you look at Y versus Z, the proportionality is their coefficient. So for this question, I put Y versus Z. For every 1 molecule of Z, I have 2 molecules of Y being produced, or twice as fast. So all I need to do is put the rate of Y here underneath and X for the rate of Z. And we cross multiply, and this becomes 40 mole per decimeter cube per second. So this is 40 mole times second minus 1, molarity rather. Now let's just go after the next question. So the next question is saying, what is the rate of disappearance of C in trial number 2? So C in trial number 2. C is a reactant, Y is a product. I only have information about Y, the product. So this time I put C compared to Y, and we see it's 3 to 2. That's the relationship. So for Y, it's 15. And this time we put the variable X for C. Cross multiply, and X is 45 divided by 2, which is 22.5. So it's 22.5 mole per decimeter cube per second as the answer for the next question. The next question is, what is the rate law from the above data? So now we have the rate expression, which is a constant K times reactants A power X, reactant B power Y, reactant C to power Z. Now let's find the experiments that at least some concentrations are constant. I go after experiment 4 compared to 3, and you see the only thing changing is C. So number 4 divided by number 3. And I'm going to do inspection, not the full calculation. So I have 0.16 for C divided by 0.08 raised to power Z is equal to 160 divided by 80. When we simplify, 0.16 divided by 0.08 is 2 to power Z equals 2. So we can say Z is equal to first order with respect to C. Now let's go after another variable as exponent. Let's see what we can find. So this time I go after experiment 2 versus experiment 1. B changes, C and A are constant. So 2 divided by 1 will say 0.03 for B divided by 0.02 for B to power Y is equal to 15 divided by 10. Simplify, 1.5 raised to power Y equals 1.5. Y is also first order with respect to B. Finally, we have one other variable. Let's go after A, and this time I go after experiment 3 versus experiment 1. A is changing, B goes away, C is changing, but I know the exponent, so we can plug it in. So experiment 3 divided by 1, 0.2 divided by 0.1 for A raised to power X. B's are constant, they go away, but C is 0.08 divided by 0.04 raised to power Z, which we know it's 1, is equal to 80 divided by 10. Let's simplify, see what we have. 2 to power X multiplied by 2 is equal to 8. So 2 to power X equals 4. So X is second order with respect to A. So the rate is equal to constant k times a power 2, b to power 1, and c to power 1. And if you're being challenged what is the overall order, just add 1, 1, and 2. That gives you overall order of 4. Now let's go after the last two questions. The next question is, what is the missing rate in trial number 5? So this is a question mark and I put X already. This time I'm going to do inspection rather than plug-in. So we are going to see what should happen to the rate when we have the following values. So it's really a comparison. So 0.2 divided by 0.05 raised to power 2, that's my fluctuation A. So don't forget this is 4 divided by 5. 0.02 divided by 0.01 raised to power 1 times 0.16 divided by 0.08 raised to power 1 is equal to 160 divided by the rate for that trial that is missing. Let's simplify it. 0.02 divided by this is 4. 4 squared times 2 is equal to 160 divided by x. So 16 times 4 is 160 over x. 64 is 160 divided by x. So we can calculate x to be 2.5 mole per decimeter cube per second. Okay, so that's the answer for that, 2.5 moles second minus 1. The last question is, what is our rate constant? And we are going to pick and choose one of the trials and just simply plug it in. And what I'm really interested in the units rather than that, so let's go after rate. And I'm going to pick and choose trial number 2 again. So for this question, what is the rate? So 15 is equal to k times 0.1 squared times 0.03 power 1 times 0.04 to power 1. And when you do the calculations and the divisions, k becomes 1.25 times 10 to minus 6. Now what is the unit? The unit for this, you should remember, is molarity 1 minus overall order times second minus 1. Overall order was 4. So this is 1 minus 4 times second minus 1. So it's molarity minus 3 second minus 1. Now molarity compared to IB is simply mole over decimeter cube. So what we can say, it's mole decimeter minus 3 raised to a power of minus 3 times second minus 1. So it's mole minus 3 times decimeter, minus 3 times minus 3 is plus 9 times second minus 1. Therefore, or I can write it up here, it's 1.25 times 10 to minus 6 mole minus 3 times decimeter positive 9 times second minus 1.